Dear student, today we learn the Joule-Thomson coefficient. This is the coefficient which is utilized for finding out whether a given gases will be cooled down or not. So Joule-Thomson coefficient gives the information regarding the cooling of a particular gases. If the Joule-Thomson coefficient is positive, this will give the cooling effect. If Joule-Thomson coefficient is negative, it will give the heating effect. So we will see how Joule-Thomson coefficient is to be determined with the help of the basic thermodynamics relations. So here there is an experiment which tell us about the Joule-Thomson coefficient. The Joule-Thomson coefficient. For performance of Joule-Thomson coefficient, there is a pipe in which a gas is to be moved. So this is the inlet of the gas, and this one is the outlet of the gas. Okay. So here, this is the porous plug. This one is the porous plug, or this one is the valve through which the gas is made to be flow from this inlet condition to this outlet condition. Here the pressure at the inlet condition, let us suppose this is the P1 and its corresponding temperature is T1. Now this gas is made to pass through this porous plug. As a result of this, the pressure of these gases will decrease from P1 to P2. But here the temperature either may increase or it may be decrease. Okay, it depends upon the Joule-Thomson coefficient. Because in this particular cases, the process is assumed to be the isenthalpic process. Here the gas is made to pass through the uniform cross-sectional tube, and this tube is equally insulated over the surface. So we will apply the steady flow energy equation here. This is the steady flow energy equation. This one is the steady flow energy equation, which says that H1 plus of V1 square by 2 plus of GZ1 plus of W is equal to H2 plus of V2 square by 2 plus of GZ2 plus of W. Here too. So here the heat which is coming out from this pipe is 0. So this value is 0. There is no any work output from this device. So the work output is 0. But we assume that the inlet and outlet velocity are the same datum. The datum are the same. The datum is the same. So this one, the Z1 and Z2 quantity is also negligible. So here we also assume the inlet velocity and outlet velocity, there is no any change of the velocity. So this particular quantity is also having the same value, and this is neglected out. So we will have a value. This is the H1 is equal to H2. So if any gas is made to pass through a insulated tubes, and that is to be operated with the help of the porous plug or the valve, and such type of process is called the constant enthalpy process, or this is called the throttling process. Here we fix one parameter. The inlet conditions is fixed and outlet condition is to be varied. So we generate a curve like this. There is a curve. This one is the curve. This one is the curve we will generate here. So here this is the inlet condition. Here we can see this was the inlet condition. This one is the inlet condition. This particular point, the gas is made to pass at a pressure P1 at a temperature T1. Okay. When the gas is made to pass through the porous plug or the valve, the pressure is to be decreased. The pressure is to be decreased due to the friction effect occurring over the flow of the gases into the porous plug. So the pressure is to be decreasing. And here the pressure, due to decrease in pressure, the temperature is increasing. Here the temperature is increasing. Here the T2 is the temperature, and this one is the temperature is further increasing. This one temperature is increasing. There is a point over which this temperature, this is the maximum temperature. After that, the temperature keeps on decreasing. So this is the curve. This is called the isenthalpic curve, and these are the various outlet points keeping the inlet conditions fixed. We can generate this curve, isenthalpic curve, by varying the inlet conditions different. Okay. So we can generate another type of the curve like this. Here, this one is the curve. This one is the curve. Another type of curve, keeping the initial condition P1, T1 are here. Now this one is the P1, T1 dash are here. Inlet condition has been different. Now the process is to be repeated same, and we generated the different enthalpy points. Both the enthalpy every enthalpy points are the same because this is the isenthalpic curve. So here we have find a maximum point here, and this one is the maximum point. We have generated another maximum point. So when we join this particular maximum point, we generate a curve that is called the inversion. This is called the inversion curve. This is called the inversion curve. And inside the inversion curve, the cooling effect is to be performed. In outside the inversion curve, this is the heating effect is to be performed. Here, this at any point at this particular curve, any point the slope is like this. Here the slope is like this. So here this slope is positive slope, this slope is negative slope, and this slope is nothing but this slope is called the mu j. Mu j, this is called the del T by del P, keeping enthalpy constant. So this particular point is represent a mu j value. So this mu j value, here the mu j value is greater and this mu j value is lesser. So this inside this inversion curve, the mu j quantity is this 0 greater value, or here at this region the mu j is the lesser value. So this region is the heating region, where how this is heating region, because the initial temperature is T1, then further when decrease the pressure the temperature has been increased, so this is the heating region. But here the pressure is decreasing further, so this one is the cooling region. So cooling and heating region is to be represented on this isenthalpic curve, and you can see here that with the help of the different diagram here, the same diagram but a different representation. See here we can see there is a different isenthalpic curve. These are the isenthalpic curve, constant enthalpy curve. Oh, this particular point, this is the maximum inversion temperature. This one is the maximum. The maximum inversion temperature indicates that if any gases whose temperature is above this maximum inversion curve, then there is no any cooling action performed on this particular gases. So for any gases that has to be cooled down, their temperature must be, initial temperature must be below this maximum inversion temperature. There, after we can say that this particular gas is to be cooled down through the Joule-Thomson effect, or the Joule-Kelvin effect. Joule-Thomson and Kelvin were the same person. So this effect can be achieved only if the temperature of the gases is below the maximum inversion temperature. Now here, this particular point, here, this is the point, this one the point, this is the maximum inversion points, and here the enthalpy, constant enthalpy curve is to be shown here by the solid line, but since the constant enthalpy curve, this throttling curve is basically highly irreversible in nature, because the frictions are involving into the isenthalpic process. So this process is highly irreversible in nature. But in this particular slide it has to be in solid line, but it is actually, this is the dotted line, because we cannot represent the any irreversible process on the property diagram. But for the convergent, the different equilibrium point to be shown here. This is the data which I have obtained experimentally, and we just connected the data. So this is the solid line represented with this. So this mu j can be find out thermodynamically with the property relations. Here we can visualize this flow of the gases. This is from the point A. Here the inlet condition of the pressure of the gas is PA, and temperature is the TA. When you decrease the pressure or by throttling actions, with the temperature has been increased. Here this is the maximum temperature. Okay, this one is the maximum temperature, and thereafter the temperature is decreased. Here you can see here the temperature, this temperature and this temperature are the same temperature, but the pressure here is very high and this pressure is very low. So the pressure are different. We have throttled the gases at the lower pressure, but there is no any decrease in the temperature of the gases. That means no cooling action is to be performed. When we just decrease the particular pressure, the same pressure is to be further decreased, then we find a decrease in temperature. This is the delta T. This is decrease. The cooling action is to be performed. So for any gases, the cooling is to be only achieved if the temperature of the gas is to be kept at this inversion points, or the pressure of this particular gas is to be made at this inversion point. Thereafter, when we just decrease the pressure, the cooling action taking place. Here this is the temperature is lower, here this is temperature is lower, this one temperature is lower. So the temperature, the cooling action is only performed when the gas is made to pass through the throttling device when the gas is at the inversion points. So maximum cooling is to be achieved when the gas is at the inversion points. So here this cooling region basically represents the gas temperature has been decreased. Here this value mu j value, this slope is the greater, so this mu j is greater than 0. Here this is the slope is the negative, so the mu j J is lesser than 0. So the mu J is positive, represent there is a cooling of the gases. Mu J is negative, this is the heating of the region. So this mu J can be find out thermodynamically with the help of the property relation. The property relations are to be given here. dH is equal to TdS plus of VdP. So this TdS, this relation can be further simplified. This is TdS is equal to Cp dt minus T del V by del T keeping pressure constant dP. Okay. So this dH, keeping the value of TdS here. So we find dH is equal to Cp dt and T del V by del T keeping pressure constant minus V dP. Okay. So when we just perform the throttling process or the constant enthalpy process, the dH comes out to be 0 value. So when we rearrange this, we find del T by del T keeping enthalpy constant is equal to 1 by Cp. This is the T del V by del T keeping pressure constant minus of V. So we will check here what should be the effect of the mu J if ideal gas is to made to pass over the pipe through the throttling process. So here there is an ideal gases which is moving through the throttling process. So ideal gases can be represented by this is the PV is equal to RT. So this can be differentiated with keeping the pressure constant del V by del T keeping pressure constant is equal to R by P and R by P further written as V by T. So putting the value here T into V by T minus V, that comes out to be 0 value. This represents that if the ideal gas is made to be passed through a tube, in that particular case there is no any change of the temperature taking place on the ideal gas. That means there is no any cooling action performed when gas is made to pass through the throttling process. But in real life there is no any gases which is the ideal gases. So every gas is the real gases. So every gases can be cooled down with the help of the throttling effects. But there is certain gases like the hydrogen which cannot be perform the cooling effects with the help of the throttling because the maximum inversion temperature of the hydrogen is very low. So here the maximum gases whose cooling is to be performed by the throttling actions having the maximum inversion temperature is in the range. That is why the maximum gases is to be cooled down by the throttling process. Okay, so this is all about of the throttling process. Hope you have understood this. Thank you.